Hello, everyone. Welcome to ECE 20002 on the 28th of June, 2022. In terms of the exam, Boyu has been working diligently trying to figure out how we're going to use the Respondus platform with the exam. It's looking increasingly likely that we're just not going to use it at all. So most likely it'll be administered very similar to a quiz. You'll get 75 minutes to complete this, quiz on Brightspace. And to that effect, the first 60 minutes are meant for working out problems. The remaining 50 minutes are meant for just, gathering your documents, scanning them if you printed them out and uploaded them, or if you're working on a tablet or something, transferring your files and uploading through the tablet. And then the exam period closes 75 minutes after it begins. So it'll be very similar to a quiz. We're trying to get a practice exam, which is just a survey up, so you can see how the workflow will go. Other than that, I don't really have too much to say administratively with the exam. If you have some sort of testing accommodation, we'll make sure that you get your added time if needed. There will be no proctoring if we don't use Respondus, which scares me a little bit. So it's going to be up to all of you, whether those of you are listening to me now or on the recording, to be very diligent. Let me know if you suspect any cheating. We want to keep this as fair as possible. Unfortunately, that means that we as the teaching staff have to rely on you, the students, to be the eyes and ears. So please let us know if you suspect any cheating. There will be some sort of, I don't want to say reward, but there will be this will be taken into account when calculating grades. I don't know. I don't want to incentivize snitching too much, as you say, but at the same time, there has to be some sort of trade-off where you get people to come forward if they suspect anything, but you don't want to have any false reports. No, hopefully no witch hunts. I don't know. We might just give you a sticker with a gold star on it and be like, yeah, something like that. Before we get started with the lecture proper, do we have any questions about material covered on exam 1? Or any questions from homework 2? Nope, no quiz this week, Jeff. You get to do an exam instead. Though if you're really disappointed, I'm sure we can make a quiz just for you. Homework parallel RCR. Let's go ahead and bring that up. Let's see if I have that downloaded already. And it's homework 2. Aubrey, Jeff's so good without a special quiz. Salem and Aubrey both want that. Okay, so let's go ahead and show problem 2. I have to actually enable screen sharing. Okay, so here was how I posed the problem. So hopefully the tricky part wasn't that you had to do it symbolically for the first 6 steps. Maybe that was for some of you, but hopefully between everything I did in the lecture, you were expecting some sort of symbolic problem incoming. So complete the following parts to formulate the differential equations for this circuit and determine its solution using classical ODE methods. So first of all, write the KCL equation for the node at VC of t. So that's this node right here above the capacitor in R3. So I always write it as currents going into the node. So I would say it would be Vn of t minus Vc of t over R2 plus C times ddt of 0 minus VC of t plus 0 minus VC of t over R3 all equals 0. So if I do that, I would have gotten this right here, where let me zoom in. No, I don't want zoom, not you zoom. I mean zoom into the document. We'll do it the browser way for now. So we get this equation right here. Like I said, Vn of t minus Vc of t over R2 minus C dVc dt minus Vc of t over R3. The next step was to rewrite the differential equation with the forcing function isolated on one side. So it's just algebra on this. So, C dVc dt plus Vc of t over R2 plus Vc of t over R3 equals Vn of t over R2. Multiply through by R2. And you notice we're just left with this. And this term has Vc of t in common, so I'll factor it out of the right. And I get, R2 times C times dVc dt plus quantity 1 plus R2 over R3 times Vc of t equals Vn of t. So this is the differential equation we want to solve. You can see we got our forcing function, a derivative, and that. As we expect, we have one reactive element, one energy storage device in this circuit. So this is a first order differential equation. So the characteristic equation can be found by the shortcut of replacing the kth derivative of Vc of t with the kth power of lambda. So this is the characteristic equation. So we'll get R2 times C times lambda plus quantity 1 plus R2 over R3 times 1. So the roots are found by setting the characteristic polynomial equal to 0. In this case, there's only one of them. So the root is just lambda is equal to negative quantity 1 plus R2 over R3 over R2 times C. And we'll notice this is very similar to the first order RC circuit that we studied, except, it's like the series RC circuit with R2, except instead of, having 1 in the numerator, we have 1 plus R2 over R3, where R2 over R3 is just a dimensionless number. So, you can imagine that if R2 is small and R3 is big, this behaves more and more like just the series RC circuit. Because we expect R3 to be big if, we don't want to short out this capacitor or, put a low resistance across it so that most of the current goes through the resistor. We want most of the current to go through the capacitor if we were designing this as like a filter or something like that, which we'll get to later on in the course. So we can see that in the limit as R3 goes to infinity, this becomes our regular RC circuit. And notice that R1 plays no part in the circuit. R1 was just a decoy to throw people off. Because, there's this voltage source across it. It's going to, draw the same amount of current, basically no matter what. It doesn't affect the operation of the rest of the circuit, R2, C, and R3. So R1 was just a decoy. R1 does not appear anywhere in any of your answers, which I thought was clever of me to do. So the homogeneous solution is a scalar multiple of e to the lambda t. So we'll get V sub CH of t is equal to A times e to the negative quantity 1 plus R2 over R3 all over R2C times t for all t greater than 0. So for the input, Vn of t is equal to V naught e to the negative alpha t u of t. The particular solution should take the form V sub C P of t is equal to B times e to the negative AT, where we just replaced, the coefficient out front with B, and it's of the form, e to the negative AT times u of t. We insert this into the ODE. After taking the derivative, we simplify further. So we get okay. It's about there's an error in my solution. Darn. I thought I was being so clever. But there's supposed to be a ddt in front of these square brackets here. R2c times ddt of b e to the negative at u of t. 1 plus r2 over r3 b e to the negative at u of t equals v1 e to the negative at u of t. You take this derivative, you just get a factor of negative a out front, and everything else stays the same. We multiply through by e to the positive at, and then we have to look at t greater than 0. So we'll get negative a r2c times b, the non-functional bits in front of here. Then we'll get plus 1 over r2 over r3 quantity times b equals v1. You get b, and you get b is equal to v1 over 1 plus r2 over r3 minus a times r2 times c. So we'll take VC of 0 plus equals 0 and write the complete solution, which again, this didn't format correctly. Huh, interesting. Well, you'll get the A part, homogeneous part, the particular part, and you say this is equal to 0, which is equal to A, and then you plug in 0 everywhere. So you get A is equal to negative B. And you get V sub C of t is equal to this. And then you plot for the values, and you should get a plot that looks like this, where it's 0 for all time up to 0, and then it turns on and does its thing. What questions do we have about this? Any questions? Straightforward, clear as mud. That V1 is V naught, right? I thought I used V1. Let me look at how I phrased the question. V naught e to the negative at. Then I used V1. Yeah, I should have rephrased the question. I'll make that V naught. Yeah, V naught is equal to V1 because I was dumb and forgot that I used a different convention for how I defined that voltage. Keaton, question 3 of homework 2. The second op-amp behave as a summing amplifier. We'll get to that later. So for E, you're just taking the result B and plugging in a new V in. No, you don't plug in V in to the complete solution part. You set the whole solution equal to its initial condition, which is 0, and then 0 is equal to the complete solution evaluated at time equals 0. You don't need to differentiate. And then let me stop sharing for a second. Let me see if I have homework 2 solution ready. Oh God, no, not that one. Not that one either. Homework 2 solution. Are you going to be able to get the solution before the exam to study? Yes, hopefully have homework 2 solution out by Wednesday, which is tomorrow. Thanks. I'll pick up use a differentiate way in the second one. I mean, yes and no. It depends on how you look at it. I will share my screen, even though you're not going to get a lot of useful information from it. So back to screen share. So here's the preview of the homework 2 solution. So there's two parts to that circuit. One is this inverting op amp, which is pretty clear. And then part 2 is a summing op amp, you know, an inverting summer. But one way to think of it is it has a regular, you know, summing component, but it has a differentiating summing component. Rather than try to identify pieces and then mix and match, you know, the parts, remember the goal isn't to just, you know, do that. It's to be able to derive these relationships on the fly. So the idea is to use KCL, you know, one time here at this inverting input and KCL at this inverting input of the second op amp. So if you do that, you get Vx minus, you know, 0, because this is 0, or you could just call it V2, and V2 is equal to 0. Vx minus V2 over Rn2 plus C times dV dt of Vn minus V2 plus V out minus V2 over Rf2 equals 0. You should get an equation like this. Plug in V2 is equal to 0, and you get this differential equation. So this is an amplifier that sums a scaled version of the input with the derivative of the input. So it adds together two parts, the input itself but scaled and the derivative of the input. And then it inverts both of them. Does that answer your question, Keaton? Could you get a switch circuit problem or two to practice? There's one on homework 3. Yeah, there is one on homework 3. There's one in the notes. I don't have too many. I think there's some in the practice exams. Speaking of practice exams, I threw up a third practice exam from spring of 21. I was like, people said they wanted more problems. I threw up one extra exam that I was able to find. I don't know. I haven't set the rubric for homework 2. I imagine you'll lose like a couple points. I don't know how many points the question is worth, so that's kind of a meaningless answer to give you. All right. Any more questions about review material? This is good stuff. So there's a Piazza post where you can request more thorough things. I have one more homework 1 problem 3A. Okay, one moment. Let me see if I can pull up this. Oh God. Oh wait, no. Keaton, I'm going to say no to that one right now, just because that's going to take a very long time. And I'm just going to say we will have to get back to that one. Maybe tomorrow's lecture. I'll try to have something ready to say. I told my TAs no more under constrained design problems where you have to choose values, but it doesn't tell you to choose a value. Like if from now on, if it tells you to choose a value, it's going to be like choose something in this range before solving the rest of the problem or something like that. Dear God, it takes forever to, because like you can choose like 2 out of the 4 resistances, any 2 of them. It just makes everything else a lot harder. So there's like how many I don't know. What's 4 choose 2? 4 times 3 divided by 2. There's at least 6 different ways to go about solving the problem. So I don't want to go through that one right now. On this exam, at the very least, there are no design questions. So I can at least tell you that there isn't really a design question to speak of, Brandon, for this one. Yeah, Mahir used the Piazza post to, put questions. So like, Keaton, why don't you put that on the Piazza post if that's something you're interested in? Is how to do homework 1-3A, which you are interested in it. So put that in Piazza, and I will whip something up to show for tomorrow. I did not write the problems for this exam. That was largely Boyu, but don't go harassing him for tips or anything like that. But to give credit where credit is due, Boyu did most of the work, making the problems for this exam. I, gave some guidance over like what topics to cover. There are 5 questions with multiple parts each. So ideally, you spend no more than 12 minutes on any single question. So there's a 60-40 split. So there's either 2 questions on lecture set 1 and 3 on lecture set 2, or there's 3 questions on lecture set 1 and 2 on lecture set 2.
So it will be similar to the homework in terms of the length of the question.
Should be shorter. Like it should be. Most of them will be shorter than homework problems. So it's not going to be like as bad as like problem 2 on homework 1, where you were constantly doing a part A and a part B, which were separate circuits. Like you'll have one problem that's like as bad as problem 2A or something like that. I do. All right. They should be about as difficult as like some of the homework problems. There's things that are hopefully there to simplify work. If you consider like adding a current source in place of a resistor, simplifying the problem, it usually saves you steps if you know what you're doing. But if you're not sure how to deal with current sources, it's going to make your good thing we only go A through F during the exam instead of A through G, Tianyan. Yeah, decided to save you from having to answer one of those subparts. The subparts are there to help you get more credit. All right. I'm going to go through another review question. Or at least something that I think would be useful. So I'm going back to lecture set 1. And a lot of people have trouble with the small signal equivalent circuit. And I've seen that time and time again on the homework. So let's go over how to do this. So the first thing you do when you get a single transistor amplifier problem is you do the DC analysis. So that's basically the first step. So you eliminate the signal source. So the AC, usually it's an AC voltage source. For the moment, you just, short it out, and you determine the DC operating point of the transistor. So that means you determine things like VGS if you need it, but most importantly, you need ID, because ID allows you to determine RO, and it's also one of the ways you can determine GM. If we go back all the way to slide 58, here are 3 different equations for GM. Well, okay, the first one's a restatement of the one at the top of the page, but Kn prime W over L VGS minus VTN, which depends on the geometry, which is usually given to you, and VOV, which you have to find. This equation depends on geometry and square root of ID. So the drain current. So again, drain current's very important to find whenever you do your DC analysis. And there's this last version of finding the FET transconductance, which is 2ID over VOV. Depends on both bias quantities. So after you've done this, you calculate the parameters of the small signal model, which is GM and RO. And then now we switch gears. So DC analysis is done. Nothing we do can change our DC analysis. We're not doing any sort of crazy Monte Carlo simulation or anything like that. So now we bring the AC signal source back, make sure it's in your small signal equivalent circuit. We eliminate the DC sources. How do we do that? Step 1, every independent DC voltage source gets replaced by a short circuit. Usually it's a short circuit to ground because one side of your DC voltage source is usually grounded. Step 2, replace each independent DC current source by an open circuit. So you experienced one of those for the first time in homework 2, problem 1. So you'll have to replace those with an open circuit. Step 3, treat large capacitances as short circuits. Step 4, treat large inductances as open circuits. Specifically at the signal frequencies that our signal source contains. Blah blah blah. That just means we don't deal with the extended frequency response considerations that we'll get to in lecture set 6. So overall, step 4, replace the transistor with one of its small signal low frequency models. Typically, you use the hybrid pi model. What does the hybrid pi model look like? I got tongue-tied. Oh, I went too far back. Here's the hybrid pi model. Where we connect G to the gate, S to the source, and D to the drain. Remember, if it's a PMOS transistor, you do not flip the polarity of anything. You just use, absolute value of VGS or absolute value of VTB or VOV or absolute value of VA and KP. So you do not flip the polarity of the voltage source or of the current source, dependent current source under any circumstances. So we have calculated GM and we've calculated RO. Alternatively, you use the equivalent T model, where one over GM appears as a resistance. And this is an I to match this I right here. You can also think of it as GM VGS, where VGS is this voltage that you must label in your diagram. If you have a dependent source, you must label the control voltage or control current somewhere in your diagram. And then you have RO. So one of these two models used, and again, for this model, G goes to the gate, S to the source, D to the drain of wherever the transistor is in the circuit. Do not flip the polarity of the source for a PMOS. Just make sure you attach to the correct gate, the correct source, and the correct drain. When do you use the equivalent T model? Use it whenever there's a resistance connected in series with the source. There's some external resistance connected to the source. It makes your analysis a little easier. You can still do the hybrid pi model, except instead of being able to determine input resistances and output resistances by inspection, you have to apply a test voltage and then measure the test current, and then take the test voltage divided by the test current to get the the equivalent resistance. Either way is fine. One's just more work than the other. If you're a purist of the hybrid pi model, keep at it. If you like the equivalent T model, and know how to use it, you might save some steps. Analyze the resulting circuit to determine the required quantities: voltage gain, input resistance, and output resistance. So what questions do we have about these steps? DC operating point capacitors act as open circuits? Yes. Because if you try to put past DC through a capacitor, you're going to have a bad time. How do you determine when to use the T model? Pi model for the win. So again, whenever there's a resistance connected in series with the source, what does that mean? So here, there's no resistance in series with the source at low frequency, so we use the pi model, or at signal frequency, so we use the pi model. See, when we attach the source, it's just ground right there. Yeah, signal ground. However, when we have this source degeneration resistor, we use the equivalent T model because, hey, we know that there's going to be this external source resistance attached to the source. Similarly with the common drain amplifier, there's a resistance attached to the source, so we'll use the equivalent T model. For the source follower, In this case, we have, this load resistance connected to the source through a capacitor. So we definitely want to use the equivalent T model to make our lives a little bit easier. Salem, you're raising your hand.
I have a question. In one of the videos I saw, the video they said I can replace the current source with the resistor if I know the voltage on that branch.
You can replace the current source with a resistor if you know the current through that branch.
If I know the voltage on that branch. Because the current source acts as a resistor, right?
No, an ideal current source is an open circuit. You can only do that trick if your current source is imperfect.
Like for example, the VGS multiplied by GM, we can replace it with 1 over GM.
That's exactly what the equivalent T model is doing.
Yes.
So that's called the source of, oh, I'm in the wrong lecture slides. Gosh darn it. Sorry, everyone, for the blitz of, slides going past your eyes. But yeah. How you go from this model to this model is you use what's called source absorption theorem, which, if the control voltage appears across a voltage controlled current source, you can just write it as, it's 1 over its transconductance. And that's how you get from this to the other. So what you're describing is how you go from the hybrid pi to the equivalent T model. Don't try to do this sort of stuff in the building the small signal circuit unless you really know what you're doing. Does that answer your question, Salem?
Yes.
Okay. So on. Why is there sometimes RO and sometimes not? The key when you're looking at these circuits is you will see something like lambda equals 0. Lambda equals 0 is the same thing as saying RO little r sub O goes off to infinity. So it's an open circuit. So you get to ignore RO. Or if you say VA with an early voltage equals 0, then what is that? No, early voltage VA equals infinity. That's the alternative way of saying you get to ignore the output resistance. It's an open circuit. RO goes off to infinity. Does that answer your question, so on? So yeah, RO becomes an open circuit when lambda equals 0 or VA to infinity. Okay. So that's just based off of the equation for RO. So you would figure that out when you did the second step of our steps on slide 69. To really hammer in these points, I want to go through the discrete source follower a little bit more. So let's see how we would make this into a small signal equivalent circuit. So let's assume we've done our DC analysis. We found the drain current, which allows us to find GM and RO, assuming we need it. We'll assume we need it for this case. We're told, lambda is equal to, I don't know, 0.02, 1 over volts. So we'll have, this is our signal source. It's AC, and then, lowercase letters, AC. And then we have R sig. And then CC1 becomes a short circuit. So lo and behold, we have this much so far. It looks the same as the original circuit. Then we'll have RG going to ground. Yep, that's the case. Now we have a resistance connected to our source terminal of our MOSFET. That means we're going to want to use an equivalent T model if you want to save work. That's what I did because I want to save work. If you're a hybrid pi purist, feel free to use the hybrid pi model. But okay, the gate of our equivalent T model is right here. The drain is this current controlled current source, and we get 1 over GM with the control current right there. So that takes us through Q1. Now VDD is a DC voltage source. That means when you want to replace it with a short circuit, and the other side of VDD is ground. So it becomes a short circuit to ground. Now, on the source side, we need to connect RS to ground because it's connected to VSS, which is a negative DC power supply. So that means it becomes a short circuit to ground as well. We need CC2 as a short circuit and RL to ground, and then VO labeled as well. That takes care of everything except we have RO in here. RO normally appears in our equivalent T model like this, where it's connected between drain and source. However, because it's connected between a place that is ground and this terminal right here at the base of 1 over GM, I moved it so that, it's connected down here. Why did I move it? So that it makes our analysis easier when we're trying to inspect the output resistance. I can do that because it went from the same potential to a place at the same potential. Ground is kind of shared through all these points in common. That was just a simplification trick. I would not probably do that on my first pass of drawing the circuit. I would probably take 2 passes to draw the circuit to make sure I got it right. And then how do I inspect this? So Rn is defined as the resistance looking to the right of CC1. We see, well, 0 current flows through the gate, so it's basically cut off from the rest. So all we see is this Rg. And then by resistance divider equation, we get that Vi is equal to Rn, which is just Rg, over Rn plus Rsig. What is the output resistance? The output resistance is the resistance looking to the left of CC2 into, this resistance right here and into the source of the MOSFET. So we'll notice we see RO, RS, and 1 over GM all in parallel. Why is 1 over GM in parallel, you might ask? Well, that's because the same current that flows through this resistance flows through this source. So by inspection, I know it's as though its other terminal were connected to ground. When inspecting resistances, you can't do that when trying to do the voltage gain. But when inspecting resistances, I know real fast that it's just going to be R naught or RO in parallel with RS in parallel with 1 over GM. And, 1 over GM is so much smaller than these other 2 resistances that I can just say it's 1 over GM. Now, what is VO in terms of VI? Well, VI is right here, which is across the 1 over GM and RS right here. So it's going to be, this resistance divider formed by 1 over GM and the parallel combination of these bottom 3 resistors. In fact, that's why it was drawn like this, was to make that very clear. So 1 over GM appears, between this top terminal of 1 over GM and ground. So it's going to be VI times the parallel combination of the 3 resistors plus over 1 over GM plus the parallel combination of the 3 resistors. And then by doing our V out over V sig, we get the following for GV. So that's how I determine GV really quickly. Do we have any questions about forming the small signal equivalent circuit or how we calculated the input resistance, output resistance, and gain of the circuit? Well, does that make a little more sense to people? I know a lot of people are really struggling with the small signal circuit and how to use it to find resistances and gain. Well, I helped at least one person. Ooh, there's a sneaky shortcut. Let's see, does the sneaky shortcut work here? Yeah. The sneaky shortcut is just, okay, yeah, you use voltage division at the output, and you have an input voltage divider. Sometimes there's sneakier shortcuts, though. Assuming everyone's good with that, I'm actually going to move on to convolution. So we'll do a little bit more convolution examples. So here we have another convolution example. So here we're going to do, last time I went pretty fast through one. Hopefully we'll go a little slower today. Find y of t is x of t convolved with h of t. Given x of t is x sub a times quantity r of t minus 2, r of t minus 1 plus r of t minus 2. And h of t is equal to h sub a e to the bt. And then I'm going to say it's times u of t. I didn't write that down, but it should be like times u of t at the end here. So by the definition of convolution, we take our first function, but now it's a function of tau, and then times our first function, or times our second function as a function of t minus tau. So HA, e to the b times quantity t minus tau times u of t minus tau d tau. So these ramp functions all are of the form like t times u of t minus 2 times t minus 1 times u of t minus 1, and then similarly for the last ramp function. So we can use the step function built into the ramp function to trim the lower limit of our integrand. So we'll integrate from 0 to infinity now, and we'll factor out all the constants towards the front. We'll break up this difference of a difference in the power, or a difference in the exponent is a product of powers, and we still have this step function sitting around. So by using the second step function, we can trim the upper limit. Remember, u of t minus tau as a function of tau is 1 for all of time, and then it steps down and becomes 0. So we can trim the upper limit is only going up to t. And xa, ha, and e to the bt are all constants with respect to our tau integral. So now we can simplify. We use integration by parts. So we'll just do the first one. So tau times e to the negative b tau d tau. So integral from a to b of u dv is integral equal to the evaluation of uv from a to b minus integral from a to b of v du. Or we're going to say u is equal to tau, and dv is equal to e to the negative b tau d tau. Remember, there's the Liate or detail rule when it comes to how you choose u and dv. We like to integrate exponentials, so we'll let that be our dv. And polynomials, we would prefer to differentiate them compared to the exponent, so we'll let that be our tau. So we'll get the integral from 0 to t of tau e to the negative b tau d tau is the integral of this, which is negative 1 over b times tau times e to the negative b tau, evaluated from tau equals 0 to t, plus the integral from 0 to t of the integral of this, which is 1 over b e to the negative b tau times the derivative of u, which is just 1 d tau. So we can evaluate this no problem. So we plug in t here. We get negative 1 over b times t e to the negative bt. And then we'll get minus 0. And then plus 1 over b e to the negative bt. Did I do that right? That doesn't look right. I think it should be 1 over b negative 1 over b squared if I integrate. Yeah. I think that's an error. Should be negative 1 over b squared e to the negative bt. Minus 1. Okay. So we'll substitute the integral evaluation into convolution 3 times and multiply by shifted step functions. So we figured it out for this term. We can expect very similar results for the t minus 1 term and the t minus 2 terms. So we'll get something that looks like this. Where, we took the original thing and then everywhere we saw a t, we replaced it with t minus 1 for the second term, multiply by negative 2 out front. And then we add a same term, but with t plus t minus 2 for all the things. And if there is an error here, I'll try to get it fixed. So here's what we had. So x of t was this, thing formed by ramps. It's actually just a little triangle function if you plot it out. Sometimes it's easier to plot it out and figure out what the convolution is like. And then our other input was this red function, h of t. And when we convolve them, we get something that looks like this. Any questions about this? As you can see, integrals are tough. We gotta watch yourself. I think I screwed up. Yes, Aubrey, thank you for answering Adrian's question. Remember to answer each other's questions on Piazza too. Like that helps you, in those borderline cases when it comes time to assign the final letter grade for the course. After we do the integral, the same integral applies just with a change of variables. So if we say t prime or tau prime is equal to tau minus 1, we can use the exact same trick here to get, the same result here. So we only have to do the work once in order to get the other two functions that make up our triangular function. Does that help you, Tianyan? Yep, you're welcome. Let's go ahead and move on and talk about the mathematical properties of convolution. So we encounter the following properties of convolution. The shifting property, we already discussed. It's our favorite property. We love to use it. Time shifting property helps us evaluate a function at a different time instant by shifting the delta function. But we also have an integration property, differentiation to convolution property, commutative property, associative property, distributive property, scalar multiplication property, complex conjugation property, and general differentiation integration property. These 5 are pretty similar to our normal properties we expect with binary operations. You probably hear them in the context of like vector spaces or with addition and addition, subtraction, multiplication, division. But let's deal with these other 2 interesting properties first and circle back to this other interesting property. So the integration property, anytime we convolve a causal function, so one that only exists, past the turn on of a step function, with the step function itself, is equal to the integral from tau equals 0 to t of x of tau d tau. So it basically says, hey, if you got this hard function and you want to figure out what its integral looks like, graphically, you can just convolve it with a step function and you get its integral. So if you convolve it for rectangular pulse, you get a sort of resetting integration. So, if you look at, the function, so we are convolving x of t with quantity u of t minus u of t minus capital T. So we get our first evaluation, and then we get our second one, which is from 0 to t minus capital T. But, this only works for, t greater than capital T. So let's see that we get integral from 0 to t of x of tau d tau. And then finally, integral from t minus capital T to t of x of tau d tau. So it basically is 0 before the causal function starts. It's the integral between 0 and capital T, and then it's resetting so that it's the integral from t minus capital T to t of the same function past the point t equals capital T. So by convolving with a unit step function, we get an integral. That's kind of nice. The differentiation of convolution property. So say we want to take the derivative of a convolution. That is equal to the derivative of the first function convolved with the second, or the first function convolved with the derivative of the second. So the derivative of the convolution is the convolution of the derivative of either function. Do not take the derivative of both functions. That's wrong with the other. You can't say this is not equal to the derivative of f of t convolved with the derivative of g of t. That's wrong. So if f of t was x of t and g of t was delta of t, the shifting property shows that dx dt is equal to the original function convolved with the derivative of the delta function. So it's kind of like the opposite of the integration property, where the derivative of the delta function is a function that is so horrendous to behold that you should avoid thinking about it lest you go insane. If you want to think about it, use the Gaussian definition of limiting sequences to get the delta function in order to approximate it. If you try to think about it using the rectangular way, you'll just drive yourself into a logical circle. So commutative and associative property. So the top equation shows the commutative property. You can choose the easier function to reflect and shift around. So f of t convolved with g of t is the same thing as g of t convolved with f of t. So whatever function is easier to reflect and shift in your head, choose that one to do. The bottom equation shows that the associative property, you can convolve with the easier function that produces the easier result first before convolving it with the third function. So f of t convolved with g of t, then convolved with h of t is the same thing as f of t convolved with g of t convolved with h of t first. And you're the viewers, so if you need proofs, look to the textbook for some guidance, but that's up to you. I'm not expecting you to prove these sorts of things. I don't think that's a good use of lecture time. So distributive scalar multiplication and complex conjugation properties. So the first property shows that we can distribute a convolution over addition. So f of t convolved with g of t plus h of t is the same thing as f of t convolved with g of t plus f of t convolved with h of t. So we distribute over addition. We can break up the convolution integral by terms. That makes sense because of how integrals work. And the convolution is defined with an integral. The middle equation shows that a times f of t convolved with g of t is the same thing as a times f of t convolved with g of t plus f of t convolved with a times g of t, where a is just a scalar. So you can just factor out scalar multipliers and deal with them at the end, kind of like we did for our example already, where x sub a and h sub a were just factored out right away. And then lastly, if we take the complex conjugate of f of t convolved with g of t, it's the conjugate of f of t convolved with the complex conjugate of g of t. And again, leaving proofs up to you. So if you take the complex conjugate of a convolution, it's just the convolution of complex conjugates. This comes up because we deal with circuits that involve complex numbers. And the last major property to discuss is this general differentiation and integration property. So above definitions to represent arbitrary derivatives and integrals. So we'll say a to the parentheses 1 of t is the same thing as the first derivative of a of t. A to the parentheses negative 1 of t is the integral from tau equals negative infinity to t of a of tau d tau. So a to the 2 parentheses 2 of t would be the second derivative. A to the parentheses negative 2 of t would be an integral of an integral. So we can change the orders of derivative integral of the functions in the convolution provided that the orders sum to 0. So f of t convolved with g of t is the same thing as the integral of f of t convolved with the derivative of g of t equals the derivative of f of t convolved with the integral of g of t. So this is a general integration differentiation property. Now you can work for a higher order, so you can make this -2 as long as this becomes a +2 and vice versa here, or 3 or 4, what have you. The orders just have to sum to 0 to get the original convolution. So this property requires that the integral be finite. You can't have an improper integral that blows up to infinity anywhere. The derivative must also go to 0 as t goes to -infinity. So you can't have, something that, is like a parabola and, over at -infinity, it's, an infinite value or any non-zero value. So we would only really use this property with the most basic causal functions that we discussed, such as impulses, steps, and ramps. What questions do we have? Not hearing any questions, let's go ahead and call lecture here. We'll discuss graphical convolution next time, as well as any additional questions you post in Piazza. So I wish you all well when studying for exam 1. Have a good day. You're welcome, everyone. Goodbye. Goodbye. Logging out.